Thank you very much, Nikhilesh sir, to accept our invitation deliver a lecture in our Sigma Xi series, lecture series. We are a small student group, although it is small now, but we are growing more. And we already had 4 to 5 lectures from various, fields, like interdisciplinary fields. And today we will have a lecture on material science subject. And Professor Nikhilesh sir is a Ransburg professor from Purdue University in the Materials School of Materials Engineering, and he's working on 4D material science, like 4D material in the sense like 3D material and combining with the time dependent study. So he will describe it in much detail. And thank you very much, sir, for accepting our invitation. So let's hear you
Okay.
here
Well,
today.
thank you very much. I think you can tell by what I'm wearing today that I'm a big supporter of Brazil. So really enjoying this World Cup. Um, hope you can see the slides.
Yes.
Yes. Okay. So thank you very much, Subhajit. It's a pleasure to be here. And I think really a special pleasure for me because I have a different connection to IIT BHU. And many of you may not know, or maybe you do know, my father is also in the field of material science and engineering and is a distinguished alum from your university and got his Bachelor of Science in 1965 and then went on to get his PhD at University of Illinois at Urbana-Champaign and had a distinguished career at the University of Alabama in Birmingham and in Brazil, where I was born. And so we have, he's emeritus now, but we've had the pleasure of working together and having a collegial relationship in addition to the usual father and son relationship. So I have a special corner in my heart for BHU. And so I just wanted to bring that up. These are some of the books that we have worked on together. So, well, let me tell you a little bit about Purdue and where I am right now. It's essentially in the Midwestern part of the United States. Our department was founded in 1938. At that time, it was called the School of Chemical and Metallurgical Engineering. And we're in the winter right now. And so top right-hand corner here, let me use my pointer. You can see a nice snowy day in the gateway that goes into Purdue University. And I'm proud to say that we were in the top 5 of the US News and World Report graduate rankings. And in material science, we're number 12 or number 13. So we're hoping to get into the top 10 in the next year or so. So that's a little bit about me. And maybe I'll just talk a little bit about what we mean by 4D material science. And we're very familiar with this materials tetrahedron. You see this in a lot of introductory material science books about the connection between processing and microstructure, properties, performance. And at the center of this tetrahedron, I would say that characterization plays a very, very important role in understanding materials behavior. And I think we're really blessed in the last 50 years or so, but particularly in the last 10 to 20 years, you've seen a real renaissance in these advanced techniques, advanced characterization techniques. I show some of these on the bottom here, all the way from stereo microscopy to X-ray microscopy, XRM, which I'll talk about today, and down to things like focus ion beam, scanning electron microscopy, where you can actually section the material with an ion beam and do micromachining and things like that. So what I'll be talking about today is characterization in 3 dimensions. And the 4th dimension here is time. So we're going to apply a stimulus to our material. It can be a mechanical stimulus. It can be an electrical, thermal, environmental, corrosive kind of stimulus. And trying to interrogate this microstructure, trying to understand how it responds to this stimulus that we're applying. And that time resolution, it can be interrupted time, it can be real time, it can be dynamic, gives us the fourth dimension. So what I hope that you'll take from this talk today is that there is a myriad of different experiments, myriad of wonderful problems that we can answer using these in situ and in operando techniques. And I'll give you a couple of examples of that. Okay, so in my group, we have several thrusts. I have some of my students and postdocs who have kindly joined today, and they're on the call as well. And so I'll just briefly go through this. We have some activity in bio-inspired materials, so looking at natural materials, things like honeycomb and sea structures, coral, things like that, cacti, and trying to understand how the structures of these materials have developed over time and how those lessons can be used to develop engineering synthetic materials. We have some activity in the microelectronics area, primarily in the area of solder and electronic packaging. So, and we'll talk a little bit today about solidification of environmentally benign lead-free solders. And then I mentioned corrosion. This is another area of interest, particularly to the US Navy, in trying to understand how metallic materials behave under corrosive environment. So this is another thrust. And then we have some other interesting things. Our postdoc Ishan Ganju is working on materials, cellular materials, foam-based materials that are used in shoes. And this is a partnership with Adidas and in their Boost foam, and trying to understand how Boost foam is essentially very flexible, very durable, very comfortable. One piece of this which has become very important, and I'll talk about this in the later part of my talk today, is the use of artificial intelligence and machine learning, and in particularly in the use of imaging. As I'll talk about today, these 4D data sets that we've talked about can be very large, and when we sit down to do the analysis and the image segmentation and things like that, particularly with respect to imaging, I would say that machine learning has a very important role to play in actually making things very efficient and helping us understand what's going on with the interplay between microstructure and external stimulus. Okay. So when we talk about X-ray tomography, you may have heard of this technique. It's been around now for a few decades. But really, I would say in the last 10 years, there have been significant advances in terms of the speed of acquisition, the resolution, and really the overall quality of the imaging that we can do. So it's primarily been used for imaging. But I'll just spend a couple of minutes talking about how it can now also be used to get crystallographic information. So things like grain orientation, grain boundary misorientation. So things that you would typically see in an EBSD polished sample, you can now actually do in three dimensions, non-destructively, and in the lab. So previously you couldn't do this in the synchrotron, but getting access to the synchrotron is something that may take a year, and maybe you'll get 3 or 4 days every 6 months. So it's not something that you can do on a routine basis. So the beauty of tomography is that it's non-destructive, and so it's really suited for these kinds of 4D experiments that that I had referred to. All right. So how does the technique work? Well, we start with the X-ray source, and your sample is sitting here. And typically that X-ray gets filtered to some degree depending upon what range of the X-ray energies we want, because in the lab this is a polychromatic beam, so multiple energies. And so we shoot the X-rays through the sample and we get a projection. Okay, so you get a projection on the screen here. And so when we rotate the sample, you can get many, many projections throughout the experiment. And so that's what I've actually shown in this particular animation. So the sample can rotate 360 degrees. At each of those angular increments can be 1/8 of an angle, something like that. We get a projection of that sample. Now, these are two-dimensional projections at different angles. And so we need to actually then do an inverse Fourier transform, what's called a filtered back projection algorithm that takes those two-dimensional projections at different angles, and then we get an inverse Fourier transform. We get a reconstruction in grayscale of our microstructure. And that particular data set at a given time can be resliced in any particular way and can be used for visualization purposes. You can take a video or something like that. But the real bottleneck, the real time-consuming part, and often the most important part, is the quantification of the microstructures. How do we describe the microstructure? How do we get statistics on the microstructure? And how do these particular parameters change over time? And for that, we need to do what's called image segmentation, which can be a very long and laborious process, but it's really very necessary to get statistics on the microstructure. So some examples might be, in this particular microstructure, the size of bismuth particles, the porosity that develops during the solidification process. In a mechanical behavior, mechanical testing kind of experiment, you may need to quantify crack density, tortuosity of the cracks. One of my students, Guilherme, is actually doing tortuosity of dendrite branches in a magnesium alloy. So things like that can be used in a very innovative way to understand the physics of the problem and exactly what's going on in that fourth dimension. Okay, so I think I've kind of gone through this. There is the acquisition portion, there is a reconstruction and an image segmentation portion that allows us to do quantification of the microstructure. And this is really where data science and machine learning comes into play. Because if we have very, very large data sets, we are doing this experiment over time, we have many, many time steps, then we have terabytes and terabytes of data. And so in order to be able to take all this data, and sometimes the most important part is a needle in the haystack, we need to be able to come up with workflows that are extremely efficient, but also accurate in quantifying the microstructural evolution. And finally, one thing that you can also do is you can take this microstructure and incorporate it into some suitable model. Most people have done some kind of a mesoscale kind of model where you can incorporate the microstructure into a finite element model, and then you can apply appropriate boundary conditions. You can apply crystal plasticity if you have grain orientation information, so on and so forth. Okay, so let me talk a little bit about the differences between synchrotron versus lab scale sources, because I think there is oftentimes some confusion in terms of what each kind of technique brings to the table. When we think about synchrotron source, these are monochromatic coherent beams, and they're also parallel in nature, okay? You can get to higher energies. I mentioned here moderate energy because most beam lines have this kind of moderate energy, but you can get to higher energy. And the biggest benefit of using the synchrotron source is that you get very high flux, so you can actually do the scans very quickly. Okay, so then you can see that the synchrotron is ideal for dynamic types of experiments, experiments that you might want to do in a fraction of a second, or certainly less than a minute. The drawback of the synchrotron, of course, is that these are massive facilities. There are very few of them in the world. In the US, we have the Advanced Photon Source, which is near Chicago. It's about a 2-hour drive from the Purdue campus. And typically you will write a proposal, and that proposal will be evaluated in terms of the quality of the science and so on. And so your access to the synchrotron can be limited. So short-term experiments every several months, and that's about it. In the lab, we have a polychromatic beam. So it's kind of a conical beam with multiple energies. And so we need to, you'll do filtration in the synchrotron too, but we definitely do filtering in the lab source so we can actually get to a range of energies that are of interest. We can get up to almost 200 keV, so we can do very high Z materials, things like tungsten, things like steel. But we overall have lower flux than what you do at the synchrotron, 3 or 4 orders of magnitude lower. Okay, so it's very amenable to longer term experiments, static experiments, and it gives you a lot of accessibility. So if we wanted to do a corrosion experiment that is going to last 1 month, 2 months, that's the kind of thing that you'd want to do in a lab scale. If you want to do a dynamic experiment, say instantaneous solidification or high strain rate, that's something you may want to do at the synchrotron. So the two techniques are really complementary to each other. And oftentimes we use them together. So for example, in some of the solidification experiments that I'm going to describe today, my student Ame Luktuke, he took a lot of these samples and actually pre-screened them in the lab prior to going to the synchrotron to make sure we had good processing, very little porosity, interesting microstructural features, different solidification conditions, and so on. So the two really can be used together, and to me, they're very complementary techniques. So let me give you an example. This is an example of heterogeneous integration in packaging. This is becoming very important as computers have many more transistors, many more I/O circuits. So 100 billion transistors in this particular Intel Ponte Vecchio package. It has some 47 active tiles. And so the point is that because we're running out of space, we need to put all kinds of different packages, all kinds of different parts of the package together. So you may have memory chip, you may have some filters, you may have the silicon, the MEMS part of the package, all sitting right next to each other, which brings up a lot of materials and mechanical based issues because these are materials that all have different coefficients of thermal expansion. They have different mechanical properties. And so when we reflow these and when we fabricate them, put them in the oven, for example, there's going to be all kinds of different strains and stresses developing there. So there's a real need for understanding what goes on in these kinds of packages, and so we've been looking at a very simple low temperature alloy, because low temperature is great when you have polymers and other low temperature materials in the package. So when we think about interconnects, when we think about metallic interconnects that are used in these packages, lower melting point is desirable. So tin bismuth has this kind of phase diagram. It's a binary. The eutectic occurs around 58% bismuth or so, and it has a melting point of around 139 degrees C. And then so there's very limited understanding of how the microstructure evolves when we go from the liquid state to the eutectic microstructure. Okay, so some of the questions we wanted to answer were, how does the microstructure evolve, and what are the mechanisms behind this phase formation? Okay, so I talked about how the tomography works but there are certainly challenges in real-time imaging, particularly related to solidification. One of them is the image quality. So the longer scan times give you better image quality. But longer times, longer exposure times also means that the experiment is going to be longer. And so a lot of these mechanisms that are taking place during solidification, nucleation of particles and things like that take place very quickly. So we want to have very good image quality, but we also want to reduce the exposure time. Okay, so if we can minimize the number of projections that we're taking during the scan, that would be better. Okay, and then we also need to get to the right range of energy that for our particular sample. In this case, we have tin and we have bismuth. Okay, so these are some of the details of the actual experiment. You have a solder foil, which is essentially melted on a copper wire. Okay, this copper wire is about 1 millimeter in diameter. And we looked at different cooling rates. Some are water quenched, some are air cooled. And these are essentially put on a resistive heater to control the temperature. And so the temperature profile looks something like this. Okay, going up, get to the melting point, and then we cool it down. All right, so these are actually from lab scale. So you just see, I think, yeah, hopefully this has an animation. Okay, actually here you can see, so this is an animation of the solder alloy. So you have the solder here is it's almost translucent. That's the tin-based phase. And then you have the bismuth particles in the red, and you have some of the tin dendrites that are forming on these particles. And the copper wire is underneath, and then you have some of this porosity. So when we were looking at this in the lab, and these are just static after solidification experiments, we noticed that these bismuth particles are tetrahedral in nature. They're almost like perfect pyramids. And the question is, why do they form that way? One thing that you do observe is that as you increase the cooling rate, so here's another animation here. This is at 1 degree C per minute. So this is the slowest cooling rate. You get larger particles, and you also get these tin dendrites that are growing on the sides of these pyramids. If you have a water quenched sample, the bismuth gets trapped in solid solution and it doesn't come out, so you don't see any bismuth pyramids formed. Okay, that's the other extreme. But in between, you can see that if we're somewhere between very slow cooling and very fast cooling, you still get some bismuth particles, but they're much larger in nature. So they're finer and they're smaller in nature, and you get more of these tin dendrite needles. Okay. So, we've quantified the volume of these bismuth particles. You can see here a volume fraction. The slower you cool, the more time you get for the bismuth to come out, and you get more of this bismuth precipitation going on. And but the real question is, how do the bismuth pyramids form? And that's something that we could not really answer using the lab scale technique. Okay, so for that we needed real-time information, real-time data showing the actual nucleation and the growth of the bismuth particles. And for that, we had to go to the synchrotron facility. So this is actually an overview of that of the synchrotron, the advanced photon source at the Argonne National Lab. Again, about 2 hours drive from where we are at Purdue. And this particular beam line is a 7 bm beam line. So we can actually do tomography And some of the data we have not processed as yet, but we also were able to collect energy dispersive spectroscopy kind of data at the beamline at the same time. Okay, and one of the nice things about this particular beamline is that it has what's called a white beam. So I told you that that typically the X-rays at the synchrotron are monochromatic, but in some beamlines we want to actually take advantage of much larger flux. And this is much more important when we get to higher density materials. So because we're dealing with tin and we're dealing with bismuth, we need much higher flux of photons, and so we use this white beam. Now, the problem with the white beam is that it has actually a distribution in X-ray energies, okay? And so we want to be able to maximize the range of X-ray energies that will give us the best contrast between tin and bismuth. Okay, so there were several parameters that had to be optimized because, again, we want to get the best image quality, but we also want to be able to scan as quickly as possible. So we started off with 800 projections and 0.4 second exposure time. So a typical scan would take about 32 seconds. So that's actually a little bit faster than the cooling rate here, which is 1 degree C per minute. So we're getting about 2 scans for every single degree change in solidification. Okay, so that's actually a good compromise. Okay. And the scanning was accompanied by real-time reconstruction. So we're scanning and reconstructing, and we're looking at the reconstructed microstructure to determine how the experiment is going. So you actually have the solder sample sitting here. It sits on a resistive heater. Again, the X-rays have to pass through and come out the other end. So this is where the X-ray beam is. You have sorry, this is the X-ray beam, and you have a shutter. And then we have this device that actually rotates, and you have a slip ring here so wires and things don't get tangled. Okay. And once the X-rays pass through the sample, then you actually have the projection. It goes through a scintillating material, which converts the X-rays to visible light, and then you have a CCD camera on the other side. Okay, so coming back to the energy range, if you look at the physics of this, this is the equation for the transmitted beam is a function of the incident beam, but we need to look at the mass attenuation coefficient. Okay, so this is the higher the mass attenuation coefficient, the lower transmission of X-rays, of course. But we're trying to shoot for, because we have tin and bismuth, we're trying to shoot for this energy range where we have the largest difference in mass attenuation coefficient. The largest difference will give you the largest amount of contrast. So we have a white beam, and we want to zero into this region between, or at least get a peak in energy between 80 and 100 kV. And so we use actually a very nice software that you can put in the type of filter, the type of material the filter is, and the thickness, and you can predict what the outcoming photon count would be. And so that's what this shows here. And we found out that for copper, we get very close to that 80 to 100 kV region. We're reducing the flux, but we're also narrowing down the energy range. So that worked out quite well. And then we did a comparison of the number of projections. So on the top left is the same sample, a section for the lab source. And on the bottom right, you have the lowest number of projections. So that would be the fastest possible scan. And we zeroed in on something like 800 projections where we could get a nice balance of efficiency, fast scanning, but still fairly good quality imaging. Okay, so so here, let me show you just a little, this is just a 2-dimensional image from a 3-dimensional scan during the solidification process. So these actually show the pyramidal bismuth particles that are growing here on the surface. And as I increase the time, you can see the temperature here, and these particles are growing. And you can actually capture the change of those particles. Now the bismuth has solidified, and you start to see the formation of the tin bismuth eutectic microstructure, which is a divorced kind of microstructure. Okay. So we go through the image analysis, and I think I have, yeah, so this is actually going from grayscale images to reconstructed microstructure. Again, the pyramidal particles are in the red, that's the bismuth. You have some porosity because of some of the flux in the solder that doesn't get burned out completely. Then you see some of that at the copper solder interface. And then you also see some of the tin dendrites that are growing off the bismuth particles. Okay, so here's actually a 4D data set. You can pay attention here to this little red dot, which is the initiation of a bismuth particle as the temperature is decreasing. And so you see that start to be a pyramid. That pyramid continues to grow. You have this little guy here, which is a neighboring particle, is also growing. And as that particle grows, they end up joining together. And you see this very nice evolution of the bismuth particles. And then, of course, tin dendrites grow. So this is some work in progress. I wanted to show that you can actually section this and get grain orientation information. So you can see that on a rhombohedral unit cell, essentially we get a preferred texture around a 1,1 kind of orientation. And we're still trying to figure out why we get this. We think, of course, it has to do with the atomic density on those particular planes and the energy of those atoms in terms when they actually join from the liquid melt. And with that, we can also study the microstructural evolution of these pyramidal particles. Okay, so we can now take measurements of these particles, and Amaya has done a nice job of looking at number of particles as a function of temperature. So you see on the red here, the number of particles that are nucleating is initially very slow, and then it goes up quite a bit, and then at the solidification or a few degrees under the solidification temperature, you start to get what appears to be some coarsening and some coalescence of these particles. And along with that, of course, you're getting more and more precipitation of the bismuth. The volume fraction of the bismuth is also increasing. So one of the things that Amaya has been trying to understand now is the kinetics of diffusion. So he's trying to separate between interface reaction controlled growth versus bulk diffusion controlled growth. And of course, if you have bulk diffusion, the crystal size should go as temperature to the 1/2. And so with the tomography data, we have quantitative 3-dimensional data as a function of time. And you can see here, sorry, trying to move this one. You can see here that we get a slope of about 0.038 or so. And actually this is 1/SV, but essentially what we're trying to point out here is n equal to 1 for interfacial reaction control growth, and diffusion control growth would be n equal to 2. So we're really close to this interfacial reaction controlled growth mechanism. So this is really the beauty of tomography, because we can get time-dependent measurements and we can fit them to either existing models, or we can refine or come up with our own models. But the nice thing is we have 3-dimensional time-evolved data, and in this particular case, it's crystal size versus temperature. Okay, and finally, you can do things like measure the growth velocity. So this is also some work in progress. So we have actually different time steps for each of these particles. And so you can measure the growth velocity at the tips of the particles. You can also measure the growth velocity at the between the liquid and the solder melt along the edge. Okay, and this is actually some data here. All right. Hopefully I'm doing okay on time. I just want to spend maybe about 10 minutes or so talking about the data science aspects of this. And here, so Subjita, am I doing all right?
Yeah, yes, sir. Yes,
okay. This particular data set was acquired at the transmission X-ray microscope beamline. It's a TXM, transmission X-ray microscopy, much lower energies, but we can get to resolutions down to about 20 nanometers or less. And so here is an example of intergranular corrosion in an aluminum alloy. And we call this data fusion because we have the imaging information, but we've also coupled this with the EBSD data. So you can see here, second phase intermetallic particles. And then you also have precipitate particles, which are actually in the blue. And then superimposed on top of that, you have grain orientations, and we could actually correlate that with the path that the intergranular cracks are taking. So precipitate density, grain boundary misorientation, and a correlation to crack growth and crack formation. So again, with these time-dependent data sets, you have very, very large amounts of data, okay? And if a graduate student were to do this in a manual way, it could take them months. So here, for example, we have MgZn2 particles. We have Al7Cu2Fe particles. We know this through EDS, what the composition is. And the background here is the aluminum matrix. So we have essentially three, actually this MgZn2 has a little bit of copper in it. So we want to be able to separate these three main phases: the aluminum matrix, the MgZn2, and the Al7Cu2Fe. These are the three main phases. Okay. So if we can do this automatically, this will really accelerate the pipeline for the image analysis and allow us to really spend more time on the thinking of the mechanisms as opposed to doing the image segmentation. Okay, so you start with a simple stack of images. You go through things like a 3D mean filter, bandpass filter, non-local means followed by an unsharpening technique there. And so what you need to do when we're thinking about machine learning is you have your 3D transmission X-ray microscopy data. This is a stack of images. And then we manually segment some of those, okay? Maybe 100 of these images we can do with manual segmentation. This set of images is then used as training for the machine learning algorithm. So we actually incorporate actual grayscale images and segmented images all together, and we put this into the training part of the machine learning algorithm. This is actually a convoluted neural network type of algorithm. And then you can actually start to look at the accuracy of the segmentation based on the area of overlap between what we call the ground truth and what the algorithm is predicting. Okay, so I want to just go over a little bit because as material scientists, at least, you know, a lot of folks don't really understand what is going on with some of these CNN models. So I think it's with any kind of machine learning model, I think it's very important to understand what's in the black box. And you may not write the code, you might be using somebody else's code, The computer scientists are definitely better than us, better than materials people at least, in developing these algorithms. But you need to understand what is going on here. Okay, so if I take this image of the number 8, I can represent this image by a matrix of numbers. Okay, that matrix of numbers will denote either a grayscale or a color intensity. All right, so I've done that. And then what I do with this particular image when I have these matrix numbers that correspond to the grayscale, I go through a convolution process. And the convolution basically filters and extracts the features of interest. Okay, and you can think of these as a matrix of 3 by 3, maybe say a kernel. Once we go through the convolution, then we actually then go through pooling. And the pooling reduces the size and essentially downsamples that image into something that is much smaller size, but still retains the information that we're interested in. So in a CNN model, you're actually going through several steps of this convolution and pooling, convolution and pooling, okay? And until we are able to really extract the features that we're interested in. So, so this is the predicted image that we get. The algorithm then compares to the ground truth, and then you can actually tweak a little bit what are called some of these loss functions to actually, you know, in a very fine way. Yeah, it's almost like taking a little tiny screw and being able to tighten that up to quantify any remaining differences. So what we really want when we're doing machine learning is to have an efficient algorithm that's able to extract the features accurately. But we also want to make the algorithm efficient by using the least number of images for training. Okay, so so here's an example of just the final result. The data set on the left, this is an aluminum copper alloy. This is something that took the student about 35 hours of a very, very small portion of the total data set. And if you use a CNN segmentation, you get the entire volume, okay, which is almost 30 times of what we were able to do in a manual sense. And most of this is automatic, okay, and takes about a day or so. Okay, so just briefly, I'll talk about some of the state of the art. This is what's called a UNet algorithm. It has a symmetric U-shaped encoder decoder. And we realized, and so the blue lines here are convolution, the green lines here are pooling, and the upsampling here is in the red. And we found actually a much nicer, more efficient algorithm called UNet++. And what the UNet++ does is it actually is multi-scale and more accurate because it actually doesn't go through arbitrary number of encoding and decoding. Sometimes you have these jump segments depending upon your data sets that can actually make this a lot more efficient. Okay, so we compared UNet, UNet++. We have better accuracy with the UNet++, but the training time is lower, and you know, we get fairly nice distribution in the MIOU here is the measurement of the area of overlap. And here you can actually see some actual images. So the raw image is on the left, and then the ground truth, which was done manually segmented, is the next column. And you see UNet and UNet++, and both do a fairly decent job. But again, the UNet++ is a lot more efficient and can be trained in a lot lower amount of time. Okay, so we can get most of the phases again, the MGZN2, the ALCUFE, and the matrix. But then the question was, do we need to actually train with all of the images that we have in the data set? And it occurred to us that, you know, when you have a stack of images from the X-ray tomography, many of the images that are very next to each other, so n+1, n+2, they're very similar. So as far as the algorithm goes, and the algorithm is like a child, a 5-year-old kid, okay? So if you teach with the same problems every time, that 5-year-old kid is not going to understand the mathematics, all right? So we need to teach with different kinds of problems. And so in this case, we need to input different, very diverse images to actually get the learning. And so we started looking at how far away from the initial image we need to get the next image, so n plus 10 or n plus 30. And as you would expect, there is a sweet spot here. So essentially, when we get to a distance between slices of somewhere between 5 to 15, we actually get no real reduction in the accuracy, but you also actually get a reduction in the training time. That's what we're looking for. All right, so that's really the point here, that we need to have unique images if you want to have efficient training of the machine learning algorithm. Okay, and we've applied this to different types of problems. This is a stress corrosion crack in a steel, and again, with the manual segmentation, this would take 120 hours. With the machine learning, we were able to get this down to about 12 hours. Okay, so I'll just play you a little animation here of the stress corrosion crack, which again, very complex, very tortuous, and really helped us understand the mechanisms and how microstructure was controlling stress corrosion cracking. Here's an example with the additive manufacturing. So in additive manufacturing, the shape of individual powder particles is very important in terms of powder flow, in terms of overall manufacturability, solidification. So we're using tomography here to get the shapes of the particles. And here we're using machine learning as a classification tool. So we go through the image analysis. This is something that Daniel Sinclair and Ishan are working on. And you get the classification, and then you can actually use different kinds of techniques to classify a perfectly a spherical particle versus one that's maybe more all oblong, more like a stick, or something that's more like a disc. Okay. So, and finally, this is some work that Ishan is doing on diffraction contrast tomography. Again, here we're actually trying to get grain orientations. And so I think using machine learning to segment these streaks is the key to getting accurate reconstruction of the grains post-processing. So here again, I think that machine learning can help us reduce the times for experiments, the times for image analysis and image segmentation, which eventually will enable us to get to diffraction contrast tomography in the lab in a 4D kind of experiment. So I will end there. I talked about, gave you an example of solidification tin bismuth solder and the evolution of these bismuth pyramidal particles, looking at things like the effect of schooling rates and things of that nature. We were able to use various different kinds of filtering, scanning parameters, real-time imaging, real-time reconstruction to be able to do this experiment in real time. And that was actually a lot of fun. And the last part of the talk, I talked a little bit about algorithm development and machine learning and how we can use machine learning and data science for actually making the process of the analysis of these images a lot less painful. So with that, I'd like to thank a lot of the folks who did the work, our collaborators and folks in the group, and our sponsors, and of course a lot of the students and postdocs whose pictures are shown here. And I'll end there, and I'll be happy to take any questions.
Thank you, sir, for such a nice talk. Yes, I think there are questions from Somuk sir.
Okay, so Professor Chawla, it's first of all, it's a wonderful talk. So I have just I don't know means whether it's a foolish one because I don't belong to material science background. So is this kind of analysis valid for other materials also?
Yeah. I mean, I think that's a good question. The machine learning algorithms are very much dependent on the quality of the data that we have, and also the types of microstructures that we're looking at. But most of this can be solved by appropriate training. So currently, we have to be able to train the algorithm with images and with ground truth from that particular system.
Okay.
Yeah.
And secondly, what I also am interested that suppose is it dependent on the, I should say, the dimension of the structure? Suppose if it is very small or if it is very large, so do you put a cap that, well, this is under my purview or beyond my purview? I don't know whether.
Yeah. No, that's also a very good question. So there I think we like to make a distinction between resolution and voxel size. So voxel size is the size of our three-dimensional imaging block or pixel. But pixel is in two-dimensional, voxels in three dimensions. So just because we can detect something, it doesn't mean that we can actually resolve what that particular constituent or phase is. So I think when we think about real resolution or real detectability of constituent phases, 3 to 4, maybe even 5 voxels is sort of a minimum necessary. Yeah. And depending upon the tool, you can get to different length scales. So the transmission X-ray microscope, we can get down to 20 nanometers. At the lab scale, or even the solidification experiments we did at the synchrotron, 1 micron is a good, true resolution.
Okay, thank you. Thank you.
I think there is a question, at least at the top of my screen. There's a hand up.
Hello, sir.
Yes.
Thank you very much for such a nice talk. I am Lavanya from IIT BHU Physics Department. As you discussed that there are dependency of cooling rate with the microstructure growth. And so at a particular rate only we are getting nice growth of microstructures, right? So is there any specific reason, like, I mean, in our lab, we also grow like single crystal or other materials, and we need slow cooling rate, and also sometimes we need like ice or air or water quench to get stuck structure, like we need to freeze a structure at the temperature. So is it similar for your case, or this is different?
Yeah, I think
For
it's
the
a little bit
microstructure
different
growth.
because these metals are in liquid form, and they're in
Yes.
bulk form. They're not thin films.
Yes.
So so the key driving force here is how does nucleation take place? It can take place by homogeneous nucleation, or you can have heterogeneous nucleation. Heterogeneous nucleation will take place at, say, a free surface or at another particle, and that can lower the free energy that is needed to get the transformation to take place. So if you notice, actually, a lot of the particles that I showed you, they are nucleating heterogeneously because they're nucleating on the surface of this solder alloy. So they're actually nucleating at the liquid-air interface. And the reason why is because at the surface of this cap, you have a lower driving force because of the heterogeneous nucleation.
Okay. So for that only we need a particular cooling rate actually.
Yeah,
To
well,
growth of nucleation.
yeah, cooling rate is the time factor, right? So slower cooling rate gives more time for diffusion. And slower, so more time for diffusion means that we can actually get the bismuth atoms to go and agglomerate and form the solid. So if you notice in the water quench case, let me go back here. The water quench case, we don't see any particles here. So bottom right, you see, we only see porosity. And the reason is that we have not given enough time for the bismuth to precipitate and diffuse out of the liquid. So it stays, it's still there, but we can't resolve it because it's actually solid solution. You know, it's trapped inside of the tin. It doesn't precipitate out.
Yes. Okay, sir. Thank you, sir.
Okay, sir, I do have some queries. What are the specification of samples, like liquid sample or thin film? Can we measure it through it?
Yeah, you can do. So this actually starts off as a liquid. You start with the solid, we heat it up, it becomes a liquid. We typically use this kind of Kapton tube because it's X-ray transparent. So in this case, we want to be able to contain the liquid as it's solidifying. But you can do these experiments in a corrosive environment. We've done experiments in 3.5 weight% sodium chloride, which is essentially seawater. You can do this at even higher temperatures. And in some of our previous work, we were able to do indentation on the sample in the transmission X-ray microscope. So you can do temperature and you can use either sharp or flat indenter to press on the sample and do the scanning.
Okay. And you have shown that the time, I mean, the resolution is like 0.4 second, right? So can we go beyond that, like in microsecond?
Yeah. You can. Again, there is that trade-off between quality of the image and how fast you can scan. So I'll actually stop sharing here so I can see all of you better. So the faster we scan, the less time we have for exposing the sample. That's where the synchrotron comes into play, because you have very large flux, you can get away with lower exposure time. Okay. And so sometimes you also need to play some tricks. So for example, if we're loading, we want to be scanning faster than the load is being applied. Otherwise, the sample will be changing while we're scanning. If we scan fast enough, then we should not be able to see any changes in the imaging during the projections.
All right.
Yeah.
Yeah.
These are great questions.
Okay. Yes. Recently, I just saw your work on honeycomb structure, right? Just yeah. So if you can just elaborate a little bit.
Yeah. Actually, Rahul is here. Rahul is the main graduate student on this work. And we published this paper on advanced materials. So the key thing there was, we had scanned, so before coming to Purdue, I was at Arizona State University. We had scanned a comb of honeybee comb at ASU. And when I came to Purdue, I started thinking about, okay, well, how do these combs actually form? And I talked to Rahul and Ishan also. And so we said, well, is there a way that we could actually see the bees making the comb? And said, well, we can't put the bees inside of the microscope because the X-rays will zap them. But there was a collaborator at the Purdue Bee Lab, Brock Harper, who's a very, very nice fellow. And he said, I can get you a colony of bees and you put them in this wooden box frame. And I said, well, maybe we can take out a piece of that frame and go to the microscope and scan it. And that's what Rahul has been doing. So So Rahul goes, he has a little slit that goes into that frame with the honeybees, and then he dutifully puts that out, goes, scans it, then puts it back after a day or so. The bees do more work, and then he goes and he scans it continuously. He's done really a great job with that. And through that, this is another kind of 4D experiment, even though it's interrupted 4D. We were able to see that the bees are actually very, very smart creatures. They actually build almost a ridged kind of spine. We call it a spine. They build something vertically. So they have stability in the structure. There's gravity pulling on this thing. It has to be balanced. Once they build a spine, then they start to grow the cells horizontally. And we were able to capture this with the tomography. So, to date, people had either looked at this with an optical microscope, or they had cut the comb and then, maybe looked at it in some other kind of microscope. But the beauty of tomography is that it's non-destructive and you can follow the change in the structure over time. So it was very well suited for this kind of work.
Yes, that was very much interesting. Congratulations to the team. Yes.
See, it's a beautiful image. That's a bismuth crystal, and actually you can buy them quite cheaply nowadays, about $50 or less now, $50 or less nowadays. Okay, and I have one. This is not mine, but I have one in my other office, not at home. And this, the not only the regularity, if you will, but the local regularity in this crystal, but then there is this multiply nucleated forms that we see. What could you investigate how they grow?
Yeah, I mean, that's what we're trying to get at. And as you say, they large clear crystals also have this kind of similar morphology, which is very interesting. What we're looking at are tiny little particles solidifying out of a tin bismuth alloy. But large deposits of bismuth also have, as you say, this kind of, very interesting patterns. So the challenge is really that, bismuth is rhombohedral. So, it's not, you have this kind of very nice crystals. And, you kind of see some kind of pyramidal formation here too, although it almost looks like it's growing in a spiral.
It is, yeah, and I mean, this is only one example, but they do have, yes, many of them have.
Yeah. So we've come across some of this work with folks in the geology area and others. But yeah, that's something that Amey is hoping to solve some of these problems before he graduates next year.
So when I talked to people who sell these things, they usually have some sort of a gem show or something like that close by. They said that these are lab grown. These are not natural.
Really?
Yeah, and that surprised me.
I'm surprised by that too. Yeah.
But the colors are fantastic. Yeah. So there must be some sort of oxidation process, something like that going on too, right?
Yes. I think there is either that or, I don't know if there's some dislocations that are forming that gives this sort of spiral morphology, but it's an interesting problem.
The colors are iridescent. I want to, make that clear. So which means that there is some sort of striation, stratification taking place. Something is there, right?
Right. Absolutely.
All right. All right. Well,
so any other question from the audience? I think, it's around 10. It's 9:40.
And it's late there.
Yeah.
Yeah. Well.
So, thank you, sir. for such a nice presentation. And really, it is new to us. Means our group in IIT-BHU, I mean, the students in the Sigma Chi chapters mostly, they are, I mean, basically material science students, like either they are chemistry people or physics or material science. They all are doing with material. So for them, it is very much informative.
That's great. That's great. No, as I said, BHU has a great name, and you guys are doing great things, and I hope some of you will continue your education, apply to Purdue for a PhD program.
Yes,
But
sure.
thank you for the invitation. It was very enjoyable.
Yes.
Thank you, Nick. But I should, however, let you know that I am an Argentina fan.
Okay. Okay. Well, we will meet you in the semifinals, hopefully.
Maybe the finals. Okay.
It's good to know. All right. Thanks, everybody.
Thank you.
Yeah.
Bye-bye.
Bye, sir.
Thanks, Subhajit.
Yeah. Thank you, sir.
I thought it went very well, right?
Yes, sir. It went very well.
Well, we'll have the next one in about 20 days. Okay.
Yes.
Okay. Wonderful. Okay. Bye-bye.
Bye, sir.
Good night, sir.